into the subject, let me start again with questions. Does anybody have questions about last class or previous classes or stuff on the book or the recitation? And I will repeat that. Yeah, yes, go ahead.
I had a few questions the other day, but I sent you some mail and got the answer, so I'm nice. I'm very good now. Thank you.
Okay, great. The question was about the center of pressure or the application point of the resultant force. And we're going to go through that now because we kind of finished limping last class. Beside that, any other question?
Yes, I have a question.
Yes.
Is there any chance from now on for the homeworks you can send like the correct answers or like a paper sheet of feedback, like to know like which mistakes I made?
Yeah.
Something like that.
I can upload easily the correct answers because that's done first, and actually I just removed the things that you should have written down, so I can do that. And maybe you can check it out on your own rather than have a particular feedback. There are a couple of persons that maybe I didn't go into each homework, so maybe there are a couple of people that I would go. And again, all the people that didn't turn in, if you need to discuss, if you couldn't open the thing or whatever, reach out. I mean, it is important that you do this. And like I said, you're probably going to have to do at least 2 more coding homeworks. And I think it's really important. I think it's an important tool for your career. So, yeah, I will upload the right answers. I was waiting for the correction to be over, and that happened yesterday, I think.
Okay, thank you.
Great. Okay, let me start with. I'm going to try to do this more interesting, and I'm going to start showing loosely related fluid mechanic topics. So hopefully you can see my screen. Yeah, I'm being asked if there are a PowerPoint of the classes. Yeah, they're all uploaded. They were uploaded before class, so you can, in Canvas, you can download them. And I'm actually not gonna go slide after slide because I think the whiteboard development is more interesting. I mean, for reading equations, you can read the book. I think the important part is to talk about them. So, so the slides are online. You can download them from there before the class if you want. Okay, anybody has an idea what this is? Currently, at this moment, there are 2 tropical storms in the Caribbean, and they're heading towards the southeast coast of the USA. Do you know what a tropical storm is? It's loosely related to, I mean, it is fluid mechanics. It's not that related to statics. They're similar to hurricanes. It just depends on the magnitude. You can see these are storms, but Marco actually yesterday was a hurricane. So it's actually slowing down. So briefly, you don't need to retain this, but briefly, these 2 are are centers of low pressure. So there are spots over the ocean where the atmospheric pressure drops. So it is smaller than in the surrounding area. And what happens is that if you have a smaller pressure, then air is going to rush in to the area where the pressure is smaller, and that's going to create winds. And on top of that, the Caribbean is the water here is kind of hot, so the air has a lot of humidity, and therefore the winds moving this water also, this air also move water, and therefore they become stronger. You don't need to understand exactly why, but basically the hurricanes feed on this humidity, and this low pressure point is moving, and it has certain patterns that depend on Coriolis and the rotation of Earth. Now, why am I showing you this? Because it is extremely rare to have two of these storms at the same time. These happen every year, and they can be with winds, very, very high winds, but it's extremely rare to have two at the same moment. So it could be that the two of them eventually interact, and that could be a never seen stuff. Actually, Marco is weakening now, but until yesterday it was kind of scary stuff. And actually, you can see this is the projection, and there was a warning here at New Orleans. This is the Mississippi mouth. All of this area could have been flood, because this will be, I will come back to this later, but when you have a low lying pressure, what happens is that the water level goes up. We've been talking about hydrostatic pressure balance. So if you have your free surface, the ocean surface, and you reduce the pressure on top of that, the water actually goes up a bit. And all of this southern USA are really low-lying areas. So if the ocean goes up 1 meter or 2 meters, that means that huge areas might flood. Especially here, here's the Louisiana, the Mississippi Delta. This is very, very low. I don't know how old were you, but here happened in Katrina some, I don't know, 10 years ago. Huge inundations in Louisiana. It was a disaster. And now, hopefully, it's very rare to have two, and hopefully they're losing energy, but this is quite scary. Why do you think we have two hurricanes at the same time? Why is this happening?
Maybe because of you said that the humidity helps. So now that we have, global warming, maybe there's more humidity, and that causes more than one hurricane, probably.
Exactly. Water warming, since the climate is changing and some waters are getting warmer, they're putting more humidity into the atmosphere, so they're creating stronger and more frequent cyclones. And this is a serious threat, not for Chile, but for many countries in the world. So, okay, this was just a topic on, let's say, hydraulics that I wanted to share. Okay, so this is the class for today. These are the slides that you could have downloaded. If you didn't, they are in Canvas. And we're gonna start here, and we didn't exactly finish last week about pressure on flat surfaces. So we're gonna start there and then extend to any surface. We're gonna talk about buoyancy and then flotation and stability. Hopefully we will finish before 7:20. So I'm gonna try to keep it short. It might be this last part might be a bit confusing. The other ones should be more or less straightforward. But feel free to interrupt me anytime. So let me try to do this. Can you see the whiteboard? Should be visible more or less. Excellent. Okay, so what we did, where we finished last time is that, let's say you had a free surface somewhere, and you have a flat surface, right? And on this surface, you're interested to compute the force into a portion of this surface. Okay, so what we did is that we said, okay, we're gonna have a system of reference where this is gonna be y, and up to the same point, this is gonna be h, the depth, And we want to know the total force here. How does it look? It looks like crap. Or do you see it pixelated like I do? Pretty good? Okay, I see it a bit pixelated, but okay. And what we said is, well, what you have to do here, we know that the pressure is proportional to the weight of the fluid. So what you need to do is you need to integrate small delta areas, right? So your total force is going to be the integral over the areas of your delta forces, and your differential forces are nothing more than the pressure over each delta area. So that should be pretty straightforward. But now the pressure is actually, well, depends on the depth. So the pressure is gamma times h times dA. But if we call this alpha, then h is just y sinus alpha. So we can remove that, and we can take gamma outside and the sinus alpha outside, and you end up with the integral of y over dA over the area. And this by definition is gamma sine alpha of y at the center of gravity times the total area, right? And this guy here is the same as the pressure at the center of gravity of the surface. The surface is going to have, at some point, here it's going to have the center of gravity. And since the pressure varies linearly, this is representative of the average pressure over the surface. So this is just the pressure at the center of gravity over the total area. You can think of this as the average pressure over the surface. All right? And that's going to be F. So we did that. And I said to you, okay, you can use this equation, but remember how you got here. Basically, you can always integrate. You can always some little contributions to the force. But if you just use blindly the equation, you might get into trouble. And this is especially true for the application point. Okay, the application point is nothing more than saying, okay, this force is going to be applied at some point, such as the torque of that force is going to be equal to the sum of all the torques of the little forces. I'm normally going to talk about torque because I think moment is a bit misleading, although it is right, it is the right word, but moment might be confused with momentum, which has nothing to do with torque, and torque is just a force times an arm, right? Okay, so the application point, we're going to call it, I don't know the name in the book, but I think it's YR. But the application point is nothing more that you say, okay, F times YR should be equal. Okay, so this was one thing. Should be equal to the integral of y times df. So you're summing every df times the arm, and that should be the same as the total force times the application point. Okay, and this, if you do the same that we did before, this is y times p, but we said already what p is. So you end up with y squared gamma sin alpha dA, right? And we know F. So the point of application is gamma seno de alpha, the integral of this, and F we know is this guy over here. So it's again gamma seno de alpha times Cg time area. Okay, so you can remove that. And here's where it gets messy. I think this is my opinion. So you can take it or leave it. But you can show that this guy here, by definition, is the wait a second, is the I forgot the word. Is the moment of inertia, right? Is the moment of inertia of this surface with respect to this. This is not a point. You can think of it as a line coming out of the whiteboard. So is the inertia of this force moving this surface around this point? All right. But you can show that. So, let me get this thing. Okay, so the moment of inertia with respect to this point is what we have here, is the integral of ys, the area. But you can show, and this I just leave it to you, that this guy is also equal to the moment of inertia with respect to the center of gravity times the position of the moment of the center of gravity square times the area. Okay, which is the same we have here. So your point of application ends up being y to the center of gravity plus the moment of inertia divided by y to the center of gravity times the area. And this, again, this is an equation that you can use directly, but you need to keep in mind a few things. You need to keep in mind that this moment of inertia represents the moment of inertia relative to this point, or to this line of the surface rotating around that line, and that these distances are measured from the free surface. Okay. Normally, when you do a weighted average of the position of the application point, you don't really mind your system of reference, because it's a weighted average. So in whatever system you're using, your results are going to be in that same system. So this equation is all right. You can use it, but you need to keep in mind that. And normally, yeah, you can say, well, but in the test, are we going to get this? Yeah, you will get it. But in real life, you don't normally have nice geometric stuff. Okay, so let me show you an example. Let me unpin this. Okay, so let me show you an example that I think is cool. Can you see the screen? So does anybody know where this is, or what this is? No, it's not Chile.
Is that the Hoover Dam, or?
It's Hoover Dam. Yes, it's Hoover Dam, near Las Vegas. So probably if you've been in Las Vegas, you probably took a trip here. I haven't. That's what I'm told. And what you see here is a dam that is collecting water behind it. I think I have another image here. So you can see, okay, this structure, the dam, it has a nice circular shape. But you can imagine that the canyon here is pretty irregular. So what's the moment of inertia of this thing? It's not straightforward to compute. Okay, so again, what it is straightforward to compute is this guy. Normally, this won't be a function. You know, here in the Hoover Dam, there is no function that defines the surface, but you know the geometry. So you could split your geometry into several bins and just compute the force in each bin, right? You could do that. So my point is, okay, you can remember these equations, but you need to keep in mind where they come from and how you get them, because in real world application, probably you won't really use them. You will go to the integration path. And just to stress the point, does anybody know where this is? No, nobody? Well, this is also a reservoir, but this one is located in Chile. This is the Puclaro, Embalse Puclaro, in the Elqui Valley, Elqui River. So it's the same idea, right? So you're blocking the water with this structure. You can Google it. I'm not sure, but they have more or less. No, this one is taller. No, it's not Brazil. It's Chile. Puclaro is taller than this one, than Hoover. But do you see any other difference? I think I have another one.
Maybe the volume of water.
Yeah, the volume. I'm not sure about the volume, because as you know, the pressure only depends on the height, right? It doesn't matter if you have a valley or the ocean behind. The pressure only depends on how deep you are, right? So I don't know what are the volumes of the water, but you can see that the structure is pretty different. Yes, this is not circular. This is actually, let's say, it has like a triangle shape, right? And the other one is, I'm sorry, and Hoover Dam is pretty circular. Do you have any idea of why? Both have roads on top, so that's not. So Hoover Dam is pretty slim. It's pretty slender, right?
The centroid of the pressure is different in each other.
Yeah, the center is different. Okay, so optimize cost, materials, all of that is true. But the main reason, because this one, Hoover Dam, I'm gonna go ahead and tell you, this is made of concrete, right? And this one, it is made of dirt, of ground, of earth, of soil. I think it's covered with concrete at some point, but it's mostly just, you know, sand, compacted sand. So you know, or you could know, concrete is way stronger than sand, but it only works nice in under compression. If you try to, if you put concrete under traction, it will fail, right? And in order to balance the pressure that this guy is generating over the dam, this dam, since it's only earth, has to be really, really large. So it's a lot larger. But yeah, maybe we couldn't build a concrete dam here. And I'm going to try to tell you why. Okay, let me go back to the whiteboard. So that's clear with these are the two equations for flat surfaces. Okay. Again, y, the coordinate, is along the surface, and from the free surface. Okay, its zero is at the free surface, and it moves along the flat surface. It assumes one angle, but it could have, well, in reality, you know, structures are not like that. So you have these two equations that you can use. But in reality, surfaces are not always flat. So I'm gonna try to draw an schematic. So let's say these are your Cartesian system, and you have a surface, whatever surface. Okay, and this surface, let's take a small delta surface element. Okay, since this is small, you can approximate it to a plane, right? And this actually, you can think of it as a vector. So this is delta S. Let's put a hat on it because it is a vector, but it has an unitary dimension. So you can think on you could project. No, this should be here. You could project this delta area into each of the each of the directions of your coordinate system. So ds actually could be dsx, and this will be a vector, dsy, there will be another vector, and ds z, this will be another vector. Okay, let me just have this this here at hand so I don't make a mistake. So you can think in the previous in the flat surface approximation, we just computed the magnitude, and we said, okay, and the magnitude is normal to the surface, right? So we didn't mind ourselves with the direction on which this resultant force is acting. We just say, okay, it's perpendicular to the force, to the surface. But if you have any given surface, yeah, the force is going to be normal to the surface, but that means that you will be able to decompose the force into each of the components. So you could say that dF should be the pressure times ds, but ds, it is a vector, so dF is also a vector, right? So you would end up with the pressure is the same. You see, the pressure is the same in every direction. We know that. So what only is going to change is how you project that pressure onto each direction. So you're going to have dfx in the I hat plus dfy in the j hat plus dfz in the k hat, right? Where each of these ones, so this guy here is the pressure times dsx, or the projection of this delta surface into the x direction or domain. So actually your resultant force is going to have once you integrate this, is going to have several components. Right? Okay, so I'm not saying anything too weird, but what does it mean? What does this imply? Well, from here, if you take x and y, what you get is that your fx is going to be the integral of p over dsx, and the same is for y. So it's the integral over sy of p over dsy. And this is the same that we just did, because each of these planes, the x and y, are flat surfaces. Okay, so basically what this is saying is it doesn't matter the shape of an object. What you only care in when you want to compute the force in one direction is which is the projection of that surface into that direction. Okay, so for instance, if we take Hoover Dam, which is something like that, right? And here you have certain elements. I don't know exactly how it is at the bottom, but let's assume it's something like that. And you have water up until here, let's say, right? So around here you have certain water. And you want to know the total force on the dam. You only need to look at from this direction. So if you look the dam from the water, you're gonna see it. You're gonna see something like that. Here are these two columns, and this is just a rectangle. So you don't mind about the circular shape. And the rectangle, we know that we only need the pressure at the half point, and the application point is going to be just below, right? We can compute that. And if you look at from the side, if you look at from this direction, you're also going to see just a rectangle, right? So if you look at from the side, this is going to be the wall, and you're going to see the dam extruding, and this is going to be the water level. So the pressure, again, is going to be this half point. And you can realize that you're going to have a pressure here and another pressure here. Of course, this one and this one are the same. They're going to cancel out. And you're only going to end up with a net force going downstream, like going down the dam. So to answer my own question, why is this circular? Because you always have perpendicular forces. So let me draw this from above. Let's say this is your dam from above. So you're gonna have several little forces, and all of them are going to be normal to the surface, right? So the dam is going to be compressed. The concrete on the dam is going to be compressed, which is where the concrete behaves best. So no part of the concrete is going to be bending. If the dam would be, okay, these are the points. If the dam would be like this, like flat surface, you would have force like that. Please realize that the net force, if this dimension is the same, this is, let's say, L, and this is also L, the net force is going to be the same. So you're going to have a net, let's say, Fn, and here is also going to be Fn. But the way it is applied is going to change how the concrete behaves. Here you're going to have a couple of torques here and here, whereas in this case you only have compression. I mean the other way around. You only have compression in your concrete, which makes this option a lot better. Now you need to have the concrete. Concrete is expensive, and you need to have a small gap here. In Puclaro, the gap is way larger, and the dam is way taller. I think it's at least 2 times taller than Hoover Dam. So you would need a lot of concrete, and to build that and to make it work so it doesn't fail is well, that's another subject, but it is not trivial at all. Okay, so that's with the horizontal forces. So if you have any shape, you only need to look at the projections of that shape over the main components, and then you can compute the forces, the horizontal forces, just as we did with the flat surfaces. Is that clear? Or was I not very clear? Okay, I'm gonna assume you're all following. Now, let me again take so whatever surface, let's take this frame of reference, and let's take, you know, whatever surface it is, and we're going to have the free surface around here. If you remember the equation that I just deleted, so f in z is going to be equal to the integral of p over dsz over z, right? And we know this is the integral of gamma h dsc, right? Why in this case is different than before? You can easily. I'm aware that we should have a break now, but let me just present this, and then we can have a break. This is slightly different than before, because the surface might cut the water twice. Okay, if this was, let me just redraw this. If this was whatever this is, but it's touching the bottom, then we only need to integrate along the top part of the surface. Okay, and indeed, in that case, what this is telling us is that if you take a small part, you need to sum h of that small part times the area, that means this volume, and multiply that by gamma. So this is just the weight, right? This is just the weight that is above this element, and if you integrate that, you end up with the weight of water above the solid. So basically, you end up with this volume, yeah, because the integral of h over the area, that's actually a volume. All right, but what happens when your object is submerged? Then a funny thing happened, and it is actually what makes the submerged bodies float. So okay, we will see that in 10 minutes. Okay, see you in a bit.
Professor,
Yeah.
can I ask you a question?
Yeah, but maybe just let me wait a few minutes so everyone's back from the break.
Okay.
Great.
Okay.
Okay. Hope everyone's back from the break. George, you had a question?
A question, yes. It's about what I asked you in Canvas in the discussion section about the negative pressure.
Yeah. Okay, so Okay, so that's not really related to this, but let's go over it. I did write a reply there,
Yes, I read it.
and I encourage everyone that has questions to post them on Canvas. So what I said there is that gauge pressure is always relative. It's relative to some reference pressure. Normally is the atmospheric pressure. So, for instance, yeah, what I said there is that the pressure on the tires of your bike is a pressure above the atmospheric pressure. So if the gauge pressure is relative, it can be negative too, because there could be a place where you have a lower pressure than the atmosphere, for example. Or it's also used in manometers and well, gauge meters, in which you measure against a pressure reference that might be the pressure on a tank or a pipe. So you can say, well, we have a drop in pressure from this tank to this other one, which might be connected through some pipes. So if you have a drop in pressure in gauge pressure, that's a negative pressure. So since it is relative, it's always a difference. So it could be negative at some point. I don't know if that
So,
makes it clear.
but if I'm measuring a pressure in a tank, and let's say that this tank, the pressure that it has is less than the atmospheric pressure. So
Yeah.
do I have to, um, is it going to be like, for example, if the pressure is 4.7, it's going to be 14.7 minus 4.7, right? That's the absolute pressure. And it's going to give me 10 psi.
Yeah. Yeah. I mean, like you say, if you have a tank and it has a lower pressure than the atmosphere,
Mm-hmm.
let's say half the pressure of the atmosphere,
Mm-hmm.
then the absolute pressure in the tank, well, that's not a good example. It has, let's say, 20% less. So the absolute pressure in the tank is 0.8 atmospheres. And the gauge meter is going to give you minus 0.2 atmospheres, however you measure an atmosphere.
Okay.
Right? So the gauge measurement can be negative,
Mm-hmm.
because gauge is always relative to a reference pressure. Now, it only depends. For instance, for a tank, it might be relevant for the structural integrity of the tank to know the difference with the atmospheric pressure. Probably you've seen this. You've seen this. This is very impressive. Let me. So this is a classic video of a tank that is being carried in a train or something. And I don't know the details, but at some point you had a sudden drop in pressure within the tank.
Mm-hmm.
And actually the atmospheric pressure collapses it.
Yeah.
So yeah, I have no idea about materials. I don't know if this is steel or whatever, but yeah. So you get, in this case, you had a negative gauge meter pressure. Okay, great.
And so when it's less than the atmospheric pressure, we have to subtract it, right? It's negative.
Yes.
But if it's above the atmospheric pressure, we have to add it.
Yeah. If you
Okay.
want the absolute pressure.
The absolute
Normally,
pressure, yes.
yeah, normally you can work with relative pressures, because for instance, the atmospheric pressure, every structure is feeling it, unless is important for some reason. Normally you can assume that the atmospheric pressure is 0, and then you work on always relative pressure. For instance, everything we're doing here about the forces on bodies, we're just assuming that the atmospheric pressure is 0, because what you're saying is that, well, this body on land it actually doesn't feel any force. We don't take the atmosphere into account, although it's pretty heavy, because it is already in balance. I mean, you can stand up, you don't feel the atmosphere, right?
Mm-hmm.
But in principle, you could add it to your own weight and do a more detailed analysis. So unless it's relevant, we can always work at least underwater with relative pressures.
Okay, thank you.
Great. Okay, so before I get back to the submerged bodies, I want to show you this. And anybody knows what this is? What this image I'm showing is? People are fleeing the class. It's not Panama, but it has to do with shipping. This is the port of Rotterdam. This is a waterway of coming. This side where you can see waves is the ocean side, and on the protected side is the port, where the port is located. And actually, these are storm barriers, because, like I said before, when you have low pressure, normally the water levels rise, and that's called a storm surge, because the water surges. And also, when you have a lot of waves, also the water rises. So these guys, the Dutch, invented these barriers. They have several barriers around the country, because the whole country is below sea level. But that's not what I want to show you. By the way, these things are massive. Here you can see people taking pictures from the hinges. They measure like more than 200 meters. I don't have the exact value, but they're massive. But what you can see is that they are round, right? Similar to what we just saw for Hoover Dam. So why do you think these are round? What do you gain? These are metal things, so you don't mind much about structural integrity, like in the concrete case. So why do you think these are round? I mean, it could be just one flat door, right? Sliding door, side to side. It has to do with the forces, to distribute the forces. Do you want to elaborate on that, or? Yes, exactly. All the forces pass through this pivoting point, because all of this, I don't know if it's an exact circular sector, but all forces are directed to this point. So it's easier to move. If the resultant force didn't pass through the pivoting point, then it would be incredibly hard to move this structure. You here almost don't have an horizontal torque. You're going to have a vertical torque, but it's going to be smaller, because as you can see, the water here is higher than here. So actually, you do have a force going out and another force going in, and all of those vertically are not going to pass in the same point, but on the horizontal, they're going to go through the same line, right? And that line passes through the pivoting points. So these are easier to move this way. Excellent. Whereas if you put a plate sliding, which they are, I mean, there are a couple of, I think in the Panama Canal, there are a couple of sluices that actually just slide one side to the other, but they're not this big. This is massive. This has, I don't know, 400 meters. So it's really, really massive. So the torques that you start feeling in your door are going to be immense. So in this way, they can actually manage to close it. Now, just a little trivia. This actually doesn't close very often. Only when you have very, very high waves and the port is at risk. Because as you can imagine, when this is closed, vessels can't get in and get out of the port. So it's bad business. So you only open it when you know it's worth the risk. Okay. back to this point. Okay, so we were saying that when you have any of any shape, basically the force on each individual infinitesimal element is going to be projected into two planes and the bottom plane, right? And the forces on the vertical planes, you can compute them just like we did before, only on the projected area. But on the vertical is a bit different, because you get this thing here of h, the area, which can translate to delta volume. So if you have a sphere, and let me just split it here, over the top part, you're going to have all this volume of water acting on it. So you're going to have, let's call this weight 1. But if you take the bottom part, this part here, and here this weight 1 is going to be acting this way. But in the bottom part, you can see that the pressure, for instance, the pressure here is proportional to the weight of all this column, regardless if this part has water or not, across the solid, I mean. Because the pressure here only depends on the vertical distance to the free surface. So you can see here that the pressure acting, the total force acting on this part is going to go upwards, and it's going to be, let's call it W2. Okay, so if Z is going to be weight 1 minus, well, it depends on the convention. Let's say upwards is positive, so minus weight 1 plus weight 2. But weight 2 is just equal to weight 1 plus gamma of water of the volume of this solid. These guys cancel out. So the vertical force is just gamma, the density of the fluid, times the volume of the solid, or the displaced volume. Okay, and it is going upwards because the pressure here, always the pressure is acting normally to the surface, right? So all around the surface you have pressures going this way. So if you cut it in half, well, weight 1 goes down and weight 2 goes up, right? And so this is I think it's pretty cool. So the force of, and this is called a buoyant force. Buoyant. I think it's buoyant. And in Spanish we call it empuje, which is a terrible word, because empuje is like pushing. So that means like laterally, and here we're buoyant, we're talking about upward. So I think it is a misleading word, but also it doesn't exist in Spanish, buoyante. You're gonna hear it nonetheless, but it doesn't exist. But they mean empuje or buoyant. Anyway, so the buoyant force is equal to the weight of water that is being displaced by the solid. Okay, and it acts upwards, or more generally against the normal weight of the fluid. If the weight goes downwards, then the buoyant force goes up, right? And this is actually what makes possible that things float, like things in water or things in the air. Okay, so let's see an example. Is this clear, or do you have any question? No, I'm being asked if parachutes work this way. No, parachutes are actually is a kinetic stuff, because actually for a parachute to work, you have to be falling, right? So it has to do with drag and turbulence, but it has to do with how are they called, the balloons work. So yeah, let's take a balloon, a typical balloon. You know that if you inflate it with your lungs, this won't go up, right? But now you can explain why. Because the rho of air, let's say, is just the same that the rho of air outside. The balloon has a small weight, right? Like the weight of the rope and the weight of the, I don't know how it's called, this plastic stuff. So if you do a sum of forces on the vertical, you're gonna have down, you're gonna have the weight of the balloon, which is really small. And up, you're gonna have the buoyant force, which is nothing more than rho air times the volume of the balloon, right? Now, this guy here, the weight of the balloon is really a small part, like let's say the weight of the materials plus also the density of air times the volume. I'm sorry, and this is going down, so this is minus, and this is plus. So these two cancel out, and you have a total negative force going down. You've probably done it in a kid's birthday. If you start putting things on the string, it will go down, right? So what they normally do is that they fill this with some other stuff, like helium, right? In that case, you're gonna have the own weight of the materials minus the rho of helium of the volume plus the buoyant force, the rho of air of the volume. So you're gonna have the weight of the materials plus, let's say, the volume, the rho of air minus rho of helium. So you can see, and this is really small. The rho of helium is really small. So if you neglect this, it's almost zero. So this is what causes the balloon to go up, right? And if the materials are really, really light, which is the idea of these kind of balloons, this will also be roughly zero. And this is why balloons filled with helium go up. And you can do the same with some other balloons, like it's not balloon the name, but there are these balloons that do meteorological measurements. They're filled with very light gases, and they actually go up very, very rapidly, and they measure all the way up. And also these balloons where you can, they have a basket and you can go around. But in that case, what is filled in the balloon is lighter air because it's hotter, right? And this is also why, for instance, submarines dive. So let me show you briefly. Let's say you have the free surface, and you have a submarine, right? And it's the same idea. The submarine has an own weight, and it has a buoyant force. Okay, and we're going to say it has a certain volume. We can neglect, here in the weight, you can consider everything, like people, the materials of the submarine, everything. So basically, the same as before. If we sum the forces in the vertical, you have the weight going down and the buoyant force going up. And the weight is going to be at some total density times the volume, and let's use density of the submarine, and this includes, air, people, everything. And the force going up is rho of water, so Okay, water times the volume. So basically, again, you have the volume times the rho of water minus rho of the submarine. So if this tidbit is larger than 0, it will go up. And if it's smaller than 0, it will go down. Now, what the submarines do, this is a very crude approximation, is that they have a ballast tank, okay, where they can pump in water. So they can fill this, a fraction of the submarine with water. With that, basically what you're doing is that you're reducing this guy. This is I'm sorry, you're making it heavier, right? Or you can consider you're reducing the volume. In any case, what you're doing is that you're turning the weight at a larger volume if this is filled with water. And if you fill it with air, because you can pump water out, you can decrease the weight. So submarines play with their own weight because the total force, well, is always the volume displaced, right? Fish do this kind of similar stuff with a certain organ that I don't remember now, but they can expand it and implode it. So they change their density in order for them to dive or go up. Now, if this sum of forces, let's say the sum of forces it's negative, you're going to have a resultant force going down. So the submarine is going to go down. Will it reach an equilibrium point? Oh, I'm being asked the same question. So you can see that if there is a total force, then the submarine is going to move down. As long as the force is there, it's going to keep on moving. So there is no equilibrium. What submarines do is that, okay, they fill these ballast tanks with water, then they start moving, and then they slowly fill them back with air. They push the water out in order to make this total force go to 0. And then they stay at that depth, right? And if they remove more water out of their ballast tank, they're going to start going up until they become neutral buoyant, okay? And this is because the rho of water is rather constant. It's rather constant along the depth. This is not the case in the atmosphere. You know that the higher you are, the less dense the air is, and therefore you have a smaller buoyancy force, right? So for a balloon, there is an equilibrium point because the higher you go, your buoyancy force is each time smaller, right? So you start really fast, and then you reach a certain equilibrium because the density of the air is changing. In water, since it's not compressible, there is a small change in density, but it's really negligible. So it's not really important. So there is no equilibrium point. So you just gotta move down your submarine and then become neutrally buoyant, and then moving up and then become again neutrally buoyant. Was that clear, or is too abstract? Now, let's talk about where these forces are applied, all right? Because I think this is pretty interesting, but it can be a bit dense. Before that, let me show you so you don't fall asleep. Okay. Can you see my screen now? Okay. Can you see the screen? I don't know if you've ever done this experiment, but you can, if you have a can of regular Coke or regular any sugary drink and one of light Coke, the one with sugar will sink, right? Both have the same volume, both have the same materials, but what changes is what's inside. So both cans feel the same buoyant force, right? Both of them are displacing the same volume, so both of them are being pushed up by the water with the same force. So the only thing changing is the weight. And the Coca-Cola, the regular Coke, is way heavier because it has a lot more sugar. Okay, I tried this with I didn't have any regular Coke, but I tried with several light beverages, and they all float. I tried it with beer too, and beer also floats because beer doesn't have that much sugar. I thought maybe the lupulus or whatever they're called in English will make it sink, but no. So it's the sugar that makes it denser, right? So again, here's to illustrate the same idea. You can look. There are several videos and images of this. Okay, but it has to do with density. The full material that it is in the regular Coke is denser than the full material that it is on the light one. Okay. Okay, so that's that. And briefly, if you have a body here, we know that the weight is applied at the center of gravity of the body, right? But where is the buoyant force applied? So we know we're going to have a buoyant force going up, but where is it applied, you think? You can obtain it the same way we've been doing this. You know, is a weighted average of the location of the force. Yes.
It is in the centroid.
It is at the same centroid if it is fully submerged. It has to be, right? Because you obtain it just as the weight of the missing fluid. So as long as yeah, there is a caveat though. If the object is uniform, then yes, they are at the same point. It might be that the object has a heavier place in another place, so the center of gravity of the object doesn't necessarily is the same as the center of gravity of the volume of the object. Yes, because the mass distribution of the object is not necessarily uniform. This is true for ships, for the submarine. So they're not exactly the same point. But if you throw a cannonball, then it's going to be the same point. If it's any other thing, especially something with air within it, then it's not going to be the same point. And that's in particularly true when you have a floating body. Okay. And this is, I think this is interesting, but it can be a bit confusing. So let's say you have a body that is partially floating on water. All right. So is floating a distance h, and this thing here has a weight w, and you have the buoyant force going up. Okay. And we're gonna say this has a dimensions L. It doesn't really matter, but we know that okay, so if you sum all the forces on the vertical, going down you're gonna have the weight, and going up you're gonna have the buoyant force. And the weight, let's forget for a moment for the depth of this. Okay, let's talk about a plane element. And the weight is going to be, again, the density of the solid times HL. I'm sorry, times, yeah, we're going to call this big H. All right. So this is big H. And the buoyant force, this is minus and this is plus. And the buoyant force is rho of water times HL. Yeah. Yeah, so we don't know exactly the relationship between these two are, but we know that if the solid is homogeneous, then the weight will be applied at the center of gravity. So the weight is going to be applied here. But the buoyant force is going to be applied on the center of buoyancy. Okay, in Spanish we call it carena, el centro de carena. And it comes from Latin, I don't know why. So you can see that the force going up is actually applied on a point located below the weight, right? So let me just redraw this so I can make it. I'm sorry, I just had a better idea. So we said this is the full body, and the weight is going to be applied here. So let me draw it just on top. And the buoyant force is going to be around here. Okay, now it's clear. Now, from a static point of view, they have to be the same magnitude. So in order for them to be in the same magnitude, what's going to change is this value. If this is very light, then this is going to be small, and if this is very heavy, then this is going to be larger, right? Assuming that this floats. Of course, if it's too heavy, it will just sink, right? So this is from a static point of view, but from a stability point of view, how stable do you think this is? Basically, you have two forces pointing to each other, but let's say you have a little wave coming in, right? So this is going to start rocking this element, and these two forces will not align anymore. All right. So in the slides you can check it out, but basically there is a small introduction of stable, unstable equilibrium, and indifferent equilibrium. I'm going to assume that you are all familiar with that, so I won't go into that. But what I need you to realize is that in this case, we have in an indifferent equilibrium in this case, and in this case we have an unstable. Because if you move this round ball, well, the center of gravity is always the same, and the buoyancy and the weight are applied in the same point. But if you move this one, then there is a chance that let me just show it. Now they're like that, but if you move them, there is a chance that they're not going to be aligned anymore, and they're going to create a torque that will turn around the full element, the full body. And if they turn it around, then it's not very stable, right? So there is a condition to check if this is more or less stable, and we're going to go into that. Before we start with that, are there any doubts? Any questions? Okay, I'm going to assume there are not. All clear, great. Let me show you, just to introduce this idea of unstable equilibrium, let me show you an example. I don't know if you've ever been into a glacier. This was in Argentina, or if you're ever seen, there is a documentary called Chasing Ice. It's really great, and they record glaciers doing what is called a calving event. A calving event is where the glacier, because it is melting, it is changing shape and is no longer stable. So what it does is the glacier tips over. So these people were on a boat and they recorded an iceberg, let's say, a piece of the glacier tipping over. So it naturally rotates to a new position which is more stable. And this happens because of the melting of the parts that are out of the water. It's pretty impressive. These things are massive, and this overturn can be very, very dangerous if you're nearby. I can't say how tall that is, but it looks a few tens of meters. And if you look at this documentary that I tell you, actually it broke off a bit. And you can see it is oscillating in this new position. And it probably, if this position is not stable enough, it will rotate back. I haven't seen the full video yet. So if you see this documentary I'm telling you about Chasing Ice, they record a huge iceberg calving. Is amazing. It's a bit terrifying. And again, it has to do, well, this is a natural process, but it has been speeding up because of climate change and global warming. Of course, you can look more of this, and also you're all familiar. You've all been in water, swimming at once, maybe in a boat, and boats are pretty stable up until you turn them on their head, right? So everything is stable up until one point, right? Okay, so I'm gonna try to do some math on this. So I'm gonna tell you right away that it is a bit harsh, but hopefully we'll get the idea. So we're gonna call this point of the center of gravity G. I'm aware that before we use CG, but you get the idea. This is the center of gravity. And this point where the buoyancy force is applied, we're gonna call it C. So normally they are aligned, right? They are in the same vertical line, and they have to be the same magnitude. They have to, otherwise it wouldn't be in equilibrium. All right, so let's say we have a small wave, and let me, for the sake of the argument, let me just remove all this line. Maybe it will make it easier to follow. Okay, so this is the free surface, right? Okay. So let's say that a wave come in, and this body rotates a bit. So I'm gonna draw the rotated body with another color. So it rotates like that. Okay. Now the new body, and so it's going to rotate around this point. Okay. So let me draw like a vertical line with respect to the bottom. So you could imagine that the center of gravity of the body is going to rotate with the body, because this is a solid body, and the center of buoyancy is going to move also here. Yes, but this is not entirely true, because as the object is rotating, it is also changing the shape that is underwater, and the center of buoyancy depends on the shape that is underwater. So the new point of the center of buoyancy will most likely not be directed here. So let's call this C1. So it will not be here, because if it was, here you would have the buoyancy, here you have the weight, and you would have a turning moment. And as soon as this thing starts moving, the very same forces will keep on overturning it. And you know from experience that's not what happens, right? So what we're going to say is, okay, let's take very small, maybe there are a lot of lines here, but let's take a very small element here. Okay, so you have this volume that comes out of the water and this volume that comes in. By definition, they have to be the same volume, right? But this new volume that is getting into the water is going to create a torque that should be equal to the torque of the new position of the buoyancy center. Okay, so let me go step by step. Okay, so these two volumes, we said we're going to call it V1 and V2. We said they have to be the same. And by definition, the new volume of buoyancy has to be the same as before, plus V1 minus V2, because these two guys are equal. And if these are the volumes, then they're going to be a new buoyancy force. We're going to put E for empuje. So E prime has to be the same as before, plus small e minus E. Again, these two are the same. So the total buoyant force is the same. But where is applied is what's going to be different. Okay. So if we take a very small element here, we just the infinitesimal buoyant force, the E of this small unit here, is going to be equal to the volume of this smaller piece times gamma. So gamma is density of water, and the height of this thing, let's call this x, and let's assume this is rotating a small angle alpha. So the height of this is going to be x times alpha times the area, which is dx times the depth of this thing. Okay, and this is the same at the other side, because this should be symmetric. So the total moment, the total moment of these little e's should be equal to x times dE over the full area. All right. And you can show that this is just gamma alpha x squared times the area times dA. I'm sorry. So you can show this is just gamma alpha and the integral of x squared dA. And this again, as we just saw, is the moment of inertia, all right, of this axis where we're assuming this body is rotating. Okay. So the moment of these little e's is gamma alpha, assuming alpha is small, times the moment of inertia of this point. Okay. But also, and let me draw this maybe more clearly. But also, if we used to have G here and C here, and now we're rotating here, G1 is going to be the same. I mean, the same distance from this point. C1 in principle could be there, but we know it's going to be located in some other position that we're going to call C gamma. So here we're going to have the weight going down, and here we're going to have the buoyant force going up prime. Okay, so the total moment is going to be equal to E prime. You get, I mean, from this drawing, the total moment is going to be equal to E prime. Let me just, to E prime times this distance, C1C. I'm sorry, C1C prime, which is this, assuming this is small, so it's this distance. And these two should be equal. Now, if we project this buoyant force into this line, it crosses into a point. And we're going to call that point the metacenter. Okay, the metacenter is the point above the center of gravity, where the buoyant force is applied, or it crosses the original center of buoyancy, center of gravity line. I know it's confusing. Normally the metacenter is just aligned with these two guys. It's going to be somewhere here, but as soon as you move it, the metacenter appears, and it will depend on where actually the buoyant force is applied, and that is going to depend exactly on the exact shape of the body. And this is actually what naval engineers do, right? So they design ships in order to get this metacenter at the right spot, so their ships don't turn around, don't turn over. Okay, and C to C1, well, we could say, well, is this very same distance from C1 to the metacenter projected with the sine of alpha. So we get that this is just the buoyant force times C1 m, the distance between, times the sine of alpha. All right, and we know that these two moments have to be the same. So let me put this here, and we also know that. So let me put this here. So we're gonna end up with gamma, alpha, and the moment of inertia around this axis, the rotation axis, should be equal to the buoyant force times C1 m sine of alpha. Okay, and here what we don't know is actually this guy. So if we solve that, C1 m, it's gamma alpha, the moment of inertia divided by force sin alpha. And if alpha is small, then alpha and sin alpha are pretty similar. All right, and we know that the buoyant force is gamma times the volume of buoyancy. So C1m is nothing more than the moment of inertia divided by the volume of buoyancy. Okay. Was that clear, or was too confusing? For me, when I studied this a few years ago, and even now, it is confusing. So I don't expect you to swallow it all at once. But basically what this is saying is that the distance from where the point is being applied and the metacenter, or let me draw this again. Let me keep that. So let me draw this again. If you have here the center of gravity and here your center of buoyancy, and this rotates to G1 and C1, there's going to be the actual buoyant force is going to be located somewhere here. We don't know. And this force is going to cut this axis at this point, M. This distance, Cm, is given by this equation. Okay? And this lets you know if your force is going to cut above the center, the weight and the center of gravity, or if it's going to cut it below. Okay? And this is going to determine if this is stable or not. Okay, let's take a 10-minute break, and we'll wrap it up when we come back. All right? Okay, hopefully you're still there. So where we left off is that, in a nutshell, when you do have a body that rotates, and we're saying this is a small angle, and a small angle alpha, the new position of the buoyant force is good. We want this position to be above the center of gravity. Why? Because if you can see here this position, if the buoyancy is here, then this couple is going to generate a torque in this direction. So if the vessel of this body is rotating in this direction, then the very same buoyancy of the body is gonna generate a restoring moment, or a restoring torque. So it will come back to its original position. In contrast, if the new position is here, you can see that this pair generates a torque in the opposite direction, in that direction. So if it starts moving, it will continue moving and it will collapse on itself. Okay. So basically you have that this distance, I'm gonna just, which is the distance between the buoyancy center and the meta center, should be larger than GZ. Let me just check so I'm not making a mistake here. Yes, and this distance we can compute it by the moment of inertia divided by the volume of buoyancy. So if this thing here that has units of meters or length is larger than the distance between the center of gravity and the center of buoyancy, then it will be stable. Stable if this happens. Okay. So what's going to happen is that this is why, for instance, if you have a raft, you know, they tend to be more stable if they are wider, if they are very, wide and not very tall. The taller it is and the narrower it is, like a kayak, for instance, the easier it's going to be to make it turn. So it's going to be less stable. All right. We won't go into much detail here because this is an art on its own. But you can see, for instance, that there is a more stable geometry given the same weight. So a way you can distribute it in order to maximize this moment of inertia. You want a surface that is hard to move, hard to tilt over water, and with a small volume. These two make more likely that the meta center is going to be above the geometric centroid of the solid. Okay, so with that, we finished the solid, the static part of the course. You should all by now have read the chapter 2, which covers these in more details, or at least more comprehensively. And we're going to start with kinematics next Monday. Like I said, probably this Friday we're gonna set up. We're gonna put up on Canvas a new homework, a new coding exercise. Related to this, to computing forces due to hydrostatic pressures. So hopefully you will find it useful, because as you've seen, we've given several equations, like one equation for a flat surface, one equation for the vertical, but you're always doing the same thing. You're computing the pressure over an area, and that's a force, and and you need to project that, and you need to sum all of those contributions over the surface of the body. So it's gonna be an exercise on numerical integration of forces, and I hope you will find it interesting. I will try to personalize it a bit, so I don't have it ready yet. In order for most of you will have to do different stuff, so you don't have a large incentive to share information. So yeah, that's that. So are there any question about the class or about the course, or any question in general? This is a good moment because you're not a lot of people left now, and it's probably easier if we just talk about rather than chatting in the email. So yeah, M is the position of the meta center. Meta center is the point of application where the new buoyant force is going to cross the original line between the buoyant center and the centroid of the body. So you want this meta center to be up. If it's above the center of gravity, then a restoring moment will be generated. If it's below, then it's gonna keep on turning on the same direction. So M is the meta center. Meta center. Okay. If there are no more questions, then okay, that's it. Thank you very much. Have a nice day. Oh, okay. Jose Tomas has one. Go ahead, Jose Tomas. I haven't seen the recitation yet, but it's probably going to be related to computing forces due to hydrostatic pressures too. But it's not going to be related to how you compute those forces on the computer or in code. Like I said at the beginning, what the coding exercise should be easy enough as long as you know the equations or as long as you understand the concepts. So the concepts should be clear here, and maybe practice a bit in the recitation. But you're not going to do any practical coding in the recitation, if that's the question. Yes, yes, because that's the second part. I've been asked if we're gonna practice the meta center stability. Yes, because that's something you haven't seen yet in the recitations, right? So probably it's gonna be a bit of that and a bit of forces on bodies generally. Okay, excellent. Thank you very much. Have a nice day.